Hey everyone, Chris here. Hope you've had a good summer. We've had a lovely long break here at Syzygy Central Command. Actually, some of us are still away, aren't we, Emily? Astronomers, always gallivanting around overseas, pretending to do work. Regular podcast service will resume again in the coming weeks. In the meantime, I wanted to share a couple of things with you. The first is a quick story about astronomers and physicists joining forces to call the universe's bluff about quantum conspiracy theories. It made me smile, and I thought you'd like it too. Second, we've set up a new way for people to help us produce this show. If you enjoy Syzygy, the very best way to show your support is still to share it with your friends and family. But if you'd like to do even more to help, then stick around to the end of this episode. So, first up, quantum weirdness, and research from MIT and the University of Vienna showing that if quantum physics is really just an elaborate trick being played on physicists, then it's a trick that the universe must have set up long before the Earth was even formed. Okay, there's a bit to unpack here. Let me explain. So, the physics of tiny things is weird. When you look at the behaviour of atoms and particles, like electrons and protons and photons of light, they do things you wouldn't expect. I don't have time to go into all the ways that the microscopic world of quantum physics messes with our intuitions. I'll put a few good links in the show notes for you to explore if you're interested. But one of the really brain-boggling bits of this quantum weirdness is a thing called entanglement. And that's when two particles, say two photons, are created in a very special state so that their properties are intrinsically tied together or entangled. One thing you can measure about a photon is its polarization, which is the direction in which its electric field is wiggling. Before you do a polarization measurement, the photon's wiggle direction is indeterminate. The particle is in a superposition. In a sense, it's wiggling in all different ways at once. It's counterintuitive, but hey, that's quantum for you. When you do the measurement, though, you somehow, we still don't understand how, you somehow force the photon to choose. Okay, it says, if you're asking, then I'm wiggling this way. But you don't know, you can't know in advance what the photon's polarization is going to be until you make the measurement. All you can say is there's a certain probability the wiggle will be in a particular direction. Quantum mechanics is all about randomness and statistics. But with an entangled pair of photons, both of these particles have these indeterminate polarizations, so you don't know in advance which way either of them are wiggling. But when you do measure one of them, and its state collapses into a particular polarization, the other photon does as well. When they're entangled, knowing one photon's wiggle gives you the other ones for free. And here's the good bit. Measuring the first photon's polarization determines the second photon's instantly, even though the second photon is somewhere else entirely by that point, maybe across the lab, maybe on the other side of the galaxy. Our measurement on the first photon has instantaneously affected the second photon across space and time. But how? Until that moment, the second photon was in this indeterminate state, but suddenly it knows what it has to be because you looked at a different photon in another place. This is what Einstein referred to as spooky action at a distance. You can tell he wasn't a fan of the whole quantum entanglement idea, a notion that seemed to violate his beloved and carefully tested theory of relativity. But if not this thoroughly un-Einsteinian spookiness, what else could explain the phenomenon of entanglement? Well, another possibility is that the random statistical nature of quantum physics isn't real. Maybe the photons really do have a specific polarization before we measure it. It's just hidden from view until the measurement is done. This idea is known as hidden variables theory. And it sounds a bit like splitting hairs. I mean, whether we don't know a photon's polarization because it's in a quantum superposition or because it's hidden from us, isn't that basically the same thing? Well, not quite. After years of heated theoretical and philosophical debate, in 1964, a Northern Irish physicist named John Stuart Bell had a breakthrough, a way to test if the world really is quantum. Bell used statistics to his advantage. He said, first, create many, many pairs of entangled photons and allow each pair to separate to two different detectors. And at each detector, you randomly choose a direction to measure each of those photons' polarizations. And when the next photon pair comes through, randomly choose each direction again and measure, and repeat many, many times. Then compare those two sets of data from the two detectors. Because of the entanglement, you'll find a relationship, mathematical correlations, between the sets of measurements. Bell's insight was that under these conditions, a hidden variables theory says that the two photons' polarizations will have a particular relationship, a specific set of correlations. A quantum theory, on the other hand, would give correlations that are subtly but measurably different. Bell's theorem, as his idea became known, was an amazingly powerful result. It allowed physicists to stop arguing and just do the experiment to see which theory is right. The first real experimental test of Bell's theorem was in 1972, and many others followed, and all of them pointed to the same conclusion. Yep, the world really does appear to follow these weird quantum rules. The photons really are entangled with a spooky but no less real connection across space-time. So that's that. Except there's a loophole. For these experiments to work, to tell quantum entanglement from just hidden stuff, you need to have a method for randomly choosing the directions that you'll measure the photons' polarizations. Otherwise, the whole experimental scheme doesn't work. But if photons can be entangled, then surely, in principle, the device that produces the photons can be too. And the lab containing the device and the experimenter operating the lab and even the device's random number generator used to decide the polarization measurements. And if that's all entangled quantum-wise, then maybe those random choices we thought we were making weren't so random after all, but just part of the whole hidden variable sleight of hand. We might think we've seen quantum entanglement, but really we're just falling for another magic trick, one that started a bit earlier in time when the whole experiment was set up in the first place. Sure, it sounds like a crazy conspiracy theory, but a tiny loophole is still a loophole. So the experimental physicists called the theorists' bluff. Look, if you're worried that we're giving the photons too much time to conspire, they argued, then we'll just base our randomized measurements on events even further back in time. How far back? In 2017, a team of researchers at MIT and in Vienna devised a system to test Bell's theorem that chose the random polarization directions from measurements of light from two distant stars, the closest of which was 600 light-years away. Their experiment showed that if there was a trick being played in the lab to make photons look entangled, then that trick had to have been set up across vast interstellar distances at least 600 years ago. Now, you'd like to think that'd be enough. But no, physicists love to go one better. And a 600-year interstellar conspiracy is still possible, right? So, in August 2018, the same team of researchers tightened that loophole even more. To select their random measurements, they used light from two distant quasars, the closest a staggering 7.8 billion light-years away. Which means either the paradoxical nature of quantum entanglement is real, and Einstein was wrong about the whole spooky action at a distance thing, or nearly 8 billion years ago, way before the Earth even existed, an elaborate hoax was set in motion involving the precisely timed emission of light from the energetic cores of two galaxies, culminating in a perversely specific joke played on some hapless physicists in a lab. Either way, the universe is pretty weird. So, that second thing I talked about at the beginning, about supporting the show? Look, Emily and I are happy you're even listening to this. We started the podcast with one goal, to share our love of all things astronomical. The more people who tune into Syzygy each week, the happier we are. So, lovely audience, if you enjoy the show and you want to show your support, the number one way you can help is to tell people about it. Grab your friends, your family members, and tell them, hey, there's this podcast you should listen to. It's called Syzygy, and it's really interesting, and it's fun, and it might blow your mind sometimes, and here's where you can find it. Just go to syzygy.fm and subscribe. If you've done that and you want to help some more, wow, you're amazing. Seriously, thank you. How about giving us a review? It only takes a few minutes. I'll put some links in the show notes on how to do that. Giving us a review means it's easier for more people to find us and share in the cosmic love. But Chris, I hear you say, we've done all of that and we still want to help you do this Syzygy thing you do. Tell us what more we can do. Okay, there is one more thing. Look, producing Syzygy each week takes time. And as Einstein proved with his theory of economic relativity, time equals money. And that's why we've launched a Patreon page. Patreon is a site where you can support your favourite creators by giving £1, a couple of pounds every month. And if even a few of our supporters did this, it would help us to cover our costs. We do what we do because we enjoy it, and we'll continue doing Syzygy no matter what. But by becoming a patron, you can help us to do it better, more often. With a bit of financial support, we can up our game and bring in really interesting astronomy people to chat to, visit exciting places where great research is going on, and devote more time to hone each episode to make it sound and look great. So, if you'd like to help us build this podcast into something even bigger and better, go to patreon.com/syzygypod. Thanks, everyone. We'll be back with more Syzygy just as soon as I can lure Emily back from her overseas gallivanting.